This is chapter 8 continued. We're going to look at, dive deeper into elimination, kind of like we did with substitution. So we did intro, compared E2 and E1, and now we're going to dive a little deeper into some things. Okay, so this is section 8.7. Okay, we're going to look at a problem here, SN1 versus E1. Okay, SN1 and E1 both have the exact same first step. That's the first line of the section, formation of a carbocation. They differ in what happens to the carbocation. And the problem is compounded here because they both have the same first rate determining step, which means the second step is fast in both cases, which means in a sense the molecule cannot differentiate between the two. So let's draw what we mean here. Okay, we have a tert-butyl bromide, a tertiary bromide. Okay, we're going to fill in these H's. We're going to have H2O excess. It's the nucleophile and the solvent. It's the base and the solvent. Okay, and we're going to get two products. We're going to get elimination. And we're going to get the alcohol. So let's kind of do a combined mechanism here. We're going to get a mixture. What we say the first step is carbocation. CH3, C, put in one of the H's, plus. There's one carbocation. Let's draw another molecule of carbocation and draw it this way. Okay, and now water can do one of two things. It can function as a weak base to give you E1 elimination, or it can attack the carbon. Again, both of these in their respective mechanisms are fast. This mechanism, again, we mentioned the substitution. We went over it in class. Let's try to abbreviate it here. What do you get is a protonated form of the product. Okay. What did we lose? We lost Br minus. We have a Br minus. Always you have a minus charge associated with the carbocation. Now the Br minus is associated with the protonated alcohol. Much like H3O plus, we have ROH2 plus. Okay. Now the bromide is not a good base. We've said this many times. The excess water will enable deprotonation. Okay. So that's that mechanism again. Deprotonation gives you the product. What's your byproduct? H3O plus Br minus in both cases. H3O plus, H3O plus Br minus. Okay, you've got to work through these over and over and over so they're like clockwork for you. So E1 is not very practical. So that's one sort of problem we have with these reactions. Okay, so 8.8 is a stereochemistry of E2. All right, E2 is much more practical, and so we can control stereochemistry. Okay, so let's look at two arrangements of a carbon-carbon sigma bond. The H and the X could be on the same side with some groups. We don't really care what these are at that point. At this point, okay, they could be H's, they could be R groups. But the idea is the H and the X are on the same side, much like cis and trans. We use terms syn and anti. Okay. Typically, syn and anti are referred to when there's a carbon-carbon single bond. We're talking about orientation. So they're on the same side. We call this syn periplanar. They're in the same plane. Okay, think of peri as same. Syn, same plane. Okay. Syn, same planar. Syn periplanar. Okay, that's what we mean. Syn periplanar. Okay. Now, we said this one earlier. Again, we introduce topics, and then we come back to them. Now they're in the same plane. Again, we don't care what exactly these groups are, but they're anti to one another. They're on the opposite face. Anti-periplanar. We explained a little bit about why this is favored. Remember, the reality here is that sp3 orbital is bound with this X in some orbital, and there is a small but important anti-bonding lobe, okay, to that orbital. It's really a whole orbital, but it's fine. Okay. So this anti-bonding lobe, this sp3 can donate some electron density, much like hyperconjugation into an empty p orbital. Okay, we can now invoke this hyperconjugation type effect. Okay, we call this the sigma star orbital. Okay, so this electron density is donating into the sigma star anti-bonding orbital. Okay. Similar to hyperconjugation. And there's another argument, and it's steric and electronic for this anti-periplanar, and all that is that the x, these delta minuses, want to be far apart for an RO minus, for example, right? There's electronic repulsion there. And there's a steric argument that the, I guess, and that's a weaker argument. Okay, so steric / electronic. So the negative charges are far apart, but this hyperconjugation effect is important. And again, I want you to understand why we talk about anti-periplanar. So let's look at some acyclic examples of the implications of this. I'm going to draw. Now I'm going to put some groups in here. Notice we have a beta hydrogen. We're using these phenyl groups as substituents. Got our lone pairs on bromine, etc. We're talking about E2 here, so let's not forget that. I'm going to just break up this charged species, even though it's ionically bound to one another, just for easier to draw. Talking about E2, we got our alpha position and our beta. Okay. I'm going to deprotonate and eliminate. It's concerted, but notice the arrangement. The H and the Br were on opposite faces of the sigma bond. They're anti-periplanar. So now look at this. This phenyl here is on the opposite faces as that phenyl. This CH3 is on the same face as the phenyl. This phenyl over here is on the same side of the, not the same carbon, the same side. And so the way we look at this is the CH3 and the other phenyl are on the same face, and the H in this phenyl. So you gotta we should build models, etc. Okay, these phenols are trans. These phenols here, the same phenols, were anti to one another. Okay, they're on the opposite sides of the sigma bond. This is where we're getting into some pretty heavy-duty concepts. Let's draw another arrangement. I'll try to avoid circling everything so that you can see it. Same idea. Okay, but we have different stereochemistry at this carbon. At the beta carbon, we have different stereochemistry. Same exact conditions. I'm going to deprotonate, kick out the bromide. The base came in here and picked that up. What do we get? Now we get the phenyl groups on the same face, the same side. Okay. Cis. Very, very important. That's acyclic. Let's look at cyclic, and specifically cyclohexanes. Okay, recall how to draw these. So if I give you something like this, right, you should be able to draw this. We said there's two chairs. There's equilibrium between the two. Vastly favored is the equatorial. And we have the less stable alkyl chloride. So less stable, more stable. Okay, that's all well and good. We've established that in the past. Groups prefer equatorial. But I am going to throw a wrinkle in. This is the one that will react by E2. How in the world does a less stable cyclohexane derivative react by E2? Well, you got to look at the alpha carbon and the beta carbon. What is the relationship between these hydrogens and the chloride? They are anti-periplanar. This is a fantastic example of kinetics versus thermodynamics. The more stable is a thermodynamic reality. It is more stable. It doesn't mean the less stable doesn't exist. Kinetically, the energy barrier to deprotonate the less stable orientation or conformation is lower in energy. Okay, the activation energy to deprotonate over here is too high in energy. So what'll happen is if it's 90 to 10 or 95.5, that 5% is going to react, and then the equilibrium will adjust. This is incredible. It's a fascinating case. Okay, so it's more reactive to E2 because of the anti-periplanarity. And the Cl, the same thing as here. Okay. So we can deprotonate like so. A base will come in here and deprotonate that. Okay, really, really interesting case. So we're only going to look at cyclohexanes for these cyclic systems, okay, in terms of these really specific anti-periplanar cases. But let's look at a disubstituted now. Okay. Okay, we're going to look at, always draw both chairs. If you're trying to figure something out, we've got a cis, and so we're going to draw two chairs. The CH3 is up here, and the Cl is up. Notice they're both cis to each other still. And then we have this equilibrium. We have one axial and one equatorial here, so let's assume these are equal in energy. Chlorines and methyls are a little different, but we're not too worried about that. So there's the chairs. Again, alpha, beta. Okay, there are two possibilities here because there's two different beta hydrogens. There's a beta over there as well. So what do we have? Let's label them A and B. A is over here. Put that one there. B was beta, so let's cross that out and call this one B. A, proton A, is this one. Only that one can deprotonate. It's going to deprotonate. It's going to push that up. And what we do is we draw a really funny looking structure. Okay, I'm going to stress that this is not a real thing because it's a trans double bond in a 6-membered ring. It does not exist. Help you draw this out. What did we do? We deprotonated over here on the original structure. And now we have this product. Minor, though. Even though there's two H's there at A, it's minor. Again, the first time you hear this, it's going to be confusing. You've got to work through it. Okay. So here, though, we're going to deprotonate at B, and those electrons are going to go up. The base is going to come up here and deprotonate, kick that out. We're going to draw our funny-looking chair like so. To help us, there is no trans double bond inside of a ring, so you can't draw that as a final product, but you can draw it to help you get there. Tri-substituted major. Remember the rule, Zaitsev rule. Okay. Notice this conformation here does not undergo deprotonation. Why? Because the chlorine is equatorial. So even though the chlorine prefers thermodynamically equatorial, kinetically it prefers axial in order to undergo elimination. This is a fantastic example of what's called a Curtin-Hammett principle. Okay, you don't need to know that, but it is. It just basically says that the lowest energy conformation is not necessarily the most reactive conformation. Okay, there's kinetic arguments, stereoelectronic arguments. Okay. All right, let's look at now. That was the cis. Let's look at the same thing but a trans. These two groups are trans to one another. So let's draw two chairs. Put the chlorine equatorial, the methyl group equatorial. That is clearly the more stable. That's all well and good. Let's do a ring flip, though. What happens? The chlorine is now axial, and the CH3 is also axial. That presents a problem thermodynamically. That maybe there's only 2% of this one, and 98% of that. But the 2%, however, is set up for a reaction. And now there's only one beta hydrogen that can eliminate, that one. This one cannot do that. So there's only one product here. The 2% is going to It's just think of it as a bottleneck. It's going to bottleneck at that 2%, but then it's going to react, and then it's going to readjust. That 98% is going to go back to 96 and 2 or whatever. It's going to slowly but surely fill in that bottleneck, react, and you're going to get this double bond. CH3 like that. Again, this is not a real thing. What we really mean is, again, you got to go back to here. What did we do? You can map on with numbers if you want. 1, 2, 3, 4, 5, 6. And then you can make 1, 2, etc. Okay, 6. And then you can say 1, 2, and 6. So where do we form a double bond? 6 and 1. Okay. This is the only product, and it's di substituted. Very tricky cases. Okay, it's the only product. There is no. So if you draw me a tri-substituted double bond, you will be incorrect on that one. Okay. All right. So that's digging deeper in terms of stereochemistry of the starting material. Let's look at 8.9. Again, you can read through the text to see this. I did the examples that are in the text to help you have go back and reference this. (8.9). When is the mechanism E1 or E2? Okay. So in substitution, we really stress the identity of the alkyl halide, right? Now, with elimination, we really need to stress the identity of the base. Okay, the base is key because both E1 and E2 increase in rate as you increase the substitution of the alkyl halide. So the base is key. A strong base is involved in the rate determining step. It will promote E2, right? So the stronger the base, the more bimolecular it's going to be. A weak base just can't, it's not strong enough to get in there. It's got to wait till the carbocation forms. So let's look at sort of an alkyl chloride, tert-butyl, so tertiary. So again, the conditions are everything. Okay? Sodium methoxide is a strong something. So it could undergo a substitution. We're going to have a whole lecture on SN2, SN1, E2, or E1, kind of deciphering between the four. But because this is a tertiary, it's never going to undergo SN2. Because it's a strong something, it's going to do something, right? It's going to undergo E2 and give you this, some byproducts that you should show, etc. However, if you have H2O excess, okay, again, now it could undergo SN1 and substitute because both are going to go through the carbocation. They dissociate. Remember, that's the rate determining step. And now you've got a weak something, so it can either deprotonate or eliminate. We kind of showed that case study at the beginning of this lecture. And so the H2O can then come in here and give the same product. Okay, so the base is key. Elimination, this is E1. All right, let's look at 8.10. I'm going to do two more topics, E2 and alkynes. So it's two consecutive eliminations. Then we're going to look at organic synthesis elimination. That'll be just a brief discussion. So 8.10, E2 and E2 reactions and alkyne synthesis. All right. Let's take a look at what happens when we have two bromides. We're going to use this phenyl again. We got a bromide and a bromide. We have the alpha and the beta. The difference is at the alpha, we have two bromides, hydrogens. You've got to have two of each. This is called a geminal dihalide. Geminal means on the same carbon. We're going to look at a vicinal. Okay. We're going to introduce another strong hindered base. They use sodium amide, which is NH2 minus, which is very similar to this, and it just has two hydrogens. It's a perfectly good base. I like to continue with the strong, the non-nucleophilic kind of trend, and we're going to see LDA a lot later. So this is a nice non-nucleophilic strong base, and we'll deprotonate twice. So we need two equivalents of that. You need two of everything, basically, two equivalents, and we're going to get an alkyne. Double elimination. That's all this is. So let's go through a mechanism. Again, they use NaNH2 as their base. Even though it's negatively charged, it just doesn't function well as a nucleophile, so it's a base. Okay. So we have LDA, lithium diisopropyl amide, that's what we call it. Same idea, deprotonation. Two consecutive E2 eliminations. There's an E2. I'm going to abbreviate the rings as phenyl. What do we get? We get a double bond, so we get what's called an alkenyl bromide. We got a byproduct here, protonated form of LDA, and what do we get? Lithium bromide. So now we can do another E2 elimination. Same idea, second equivalent deprotonates, forms a triple bond. Okay, so not so different, forms an alkyne. And of course you get the same byproducts, so you can fill those in. E2, E2. Let's show a vicinal dihalide, so the bromides are just on opposite carbons, same idea. Now, in a sense, we have two alpha carbons and two beta hydrogens. Okay, it's just going to do the same thing twice. We can go back to our potassium terbutoxide, two equivalents of that. You can always ask me. You can actually stop at the alkenyl bromide with one equivalent, probably in principle. It's a little harder to do the second one, but we're mainly focused on making alkynes. Here, same idea. Minus charge, potassium. It's going to go over there and deprotonate either of these. Find first. Oops, sorry, scratch that. And then it's going to happen again. So you can fill that in. Deprotonation, second time, gives a second byproduct of terbutyl alcohol, right? Alcohol, and you got potassium bromide. So vicinal, it's just the same idea. It's just they're on different carbons. So let's look at organic synthesis with elimination. Okay, now we know another reaction that we can do. Okay, so the question is, how do you make this? Right? I kind of said that before that or whatever this thing is. It's a backwards arrow. It's a retrosynthesis arrow. So we'd ask the question, how do we make this? And now we know. We make it from alkyl halides, chlorine, bromine, iodine. Just so you see this, it's sort of a preview of chapter 15, long way off, okay, maybe, but you can replace that H with an X if you use Br2 and heat or light, for example. We'll see this. This is radical chemistry, chapter 15. You just want to put that in your mind. Okay, so I'm running this test. That way you can kind of see that's how you make a bromide. Okay, you can do that with bromine and chlorine. We'll talk about that later. But just so you know, you can take things like cyclohexane, alkenes, make the bromide. Okay, so we're talking about forward sense, bromine and light, or bromine and heat, make the bromide. And then in the forward sense, what do? You use potassium tertiary oxide or something like that. DBU, DBN, LDA, etc. We didn't talk about LDA for double bonds, but you get the idea. Same thing for alkynes now. How would you make an alkyne? We'll see these are very useful. Terminal alkynes are very useful. So how would you make those? You could say NaNH2, LDA, okay, potassium tert-butoxide, one of these non-nucleophilic bases. And how do you make that? There's a couple different options, and you'll see that there's flexibility. Okay. You could have this geminal dibromide, or you could have this dibromide. Okay. The H's are implied. So retrosynthesis is very powerful. We want to keep introducing it. There will be potentially a question or two on those, but keep reviewing your reactions, etc. And that is the third lecture. We'll have one more lecture on Chapter 8, which will address this pressing question of when do you know when it's SN2, SN1, E2, or E1. We're going to talk about all four, so we're going to kind of combine 7 and 8. Okay, so we'll see you next time.